Hello, I'm Channa Bankapur. I'm going to discuss my solution to today's problem in October Lead Coding Challenge. And today's problem is inserting a value into a binary search tree, BST. Um, the property of BST is the value of root node is greater than the value of all the nodes in the left subtree, and the value of the root node is less than the value of all the nodes in the right subtree, right? So that's the property of the BST, and that is useful in searching for a node. Say for example, I want to search for say 3 in this. 3 is less than 4, I go to the left, and it is greater than 2, so I go to the right here, and it is equal to 3 here, so we found it, right? So that's how we normally search. Suppose I want to search for 5. 5 is greater than 4, so I'm going to go to the right side, and it is less than 7. I need to go to the left side, but it is null, so therefore 5 is not present. That's how we're going to find. So suppose now, if I want to insert 5, so I should be able to search for it later, right? So this is how I'm going to search. So this is a valid place for 5, right? So that's where I'm going to insert 5, and so that when you search for it the next time, it is going to be easy, all right? So the solution is that simple. You just traverse through as if you're searching for that value, and whenever you hit a null, so that's the place you need to insert. So this is a recursive solution. That's why when you go to the bottom there, when you go to that null place, this is how it looks like, right? So where root is null, when root is null, that's where you're going to insert, and you call that as the root, right? And return root, right? If it is not null, that means you're still going down the tree. If the value, whatever you're inserting, is less than the root value, so obviously you need to insert to the left side. You insert to the left side here recursively, and then assign that value, the root's value, to left of root, right? Similarly, in the other case, you insert to the right side and then assign it to the right. So in any of the cases, you got to return root anyway, so we're returning root, right? So this is the simplest way of inserting a node into a BST, and it should work. So let me quickly submit it, and then it is accepted, right? So it runs pretty quickly also. If you want to know what is the time complexity of this, suppose if there are n nodes in the tree, it's not just about n which is dependent on. Suppose if there are n nodes, and height of the tree is h, right? H is the height of the tree. Height is essentially the longest path from root to a leaf, because we either go to the left or right, but not both. Both. It's going to take a big O of h as the time, because that's the upper bound. The upper bound time is dependent on height of the BST. Obviously, a general BST can have height itself in the art, uh, in big of n. So that's why we can say this algorithm is big of n, right? If height is something you need to care for, it's going to be big of h, right? So that's how simple this problem is. Hope you liked it. If there is anything to comment, please do share it, right? Happy coding. Thanks for watching.